you. This is Bar-Cohen, Yosi from Jet Propulsion Lab, and my presentation is about deep drilling using the biologically inspired Gopher. And I would like, in the opening of my presentation, to thank Professor Ricardo Scoli for suggesting this method of recording and for making this presentation on my behalf. I'm sorry that I could not be in Italy. I wish I could, but at least I have this opportunity to make this presentation for you. This is a work that represents a team effort between my group at JPL and Honeybee Robotics, which is a company not too far from our facility. And we have been developing this drill that is driven by piezoelectric actuator. The reason why we're developing it, we're trying to help NASA with the exploration missions to develop methods of acquiring samples for doing in situ analysis or for samples that will be brought back to Earth. This objective is trying to search for evidence of life and possibly other resources like water and mineral, hopefully, and as well as trying to understand the history of the solar system. Deep drilling is quite important for such missions as to go to Mars or flagship missions to Saturn moon, like Titan and Europa, which are icy moons of Jupiter. The topic of deep drilling is quite a challenge, and so far the drilling that were done on Mars has been on missions like Phoenix Scout and the Mars Science Lab MSL. And basically, the drilling depth has been 5 centimeters, and that has been a challenge. What we are hoping to do is basically drill much deeper, reach beyond 2 meters deep, in order to access pristine samples. Because what we expect is that the UV and radiation have reached this far as 2 meters. So we're trying to see if we can drill deeper. Here is a view of, you probably have seen it on TV, that we had the Curiosity, and which is interesting. It is somewhat biologically inspired because it is like the spider coming on its own string from branches of trees and whatever. And you can see the rover that was sent after it is landed and started exploring Mars. As far as this Gopher, it's a way to make holes. You can see a Gopher on the left. Basically, the Gopher grab soil and throw it out of the hole and keep going. Drill is basically doing the same thing. It is a wireline type drill, and basically it drill into, create a hole and create fragments. The fragments are removed and brought to the surface, and it keep going. It consists, as you can see in this picture, of an anchor that allow to perform rotation, because it's combining rotation and hammering, and also allow to have wet-on bits so that it can push independent of gravity. Like Europa gravity is about 1/6 of Earth, and other places like Mars has 1/3 of the gravity on Earth. So we do not want to depend on gravity for this effort. But the key is to allow to rotate the bit. So we have a rotation system shown, but we also have a hammering, and the hammering is provided by a piezoelectric actuator. And then we have the bit, and that the Gopher 1 that is shown on the right, we use the coring bit to create the core. And you can see that we put them in tubes, and we created something like 32 cores over a distance of 3 meters. To understand the mechanism, we distinguish between conventional approaches of drilling and wireline. Ours is wireline type. You can see illustration of the height of what we are making. It's somewhat higher, longer, taller than human. We're talking about something like 2-meter drill, and basically it goes in, create fragments, and they are brought up to the surface using cable. So the only thing that is needed to go great depth is just longer cable, which is an advantage, as opposed to the conventional approach where we need a mechanism of adding strings. The strings can be heavy if we have if we want to be able to reach the great distances. They have to be also quite stiff to be able to sustain that. So the advantage of the wireline type is it is much lighter mechanism as a whole, as a system, and it has less complicated mechanism of downloading. Basically, just a pulley that allows the lowering of the cable, and of course it can reach quite large depths with relatively compact system. The mechanism of the piezoelectric actuation has been demonstrated in, and you can see a picture on the right. Basically, it is vibration of a piezoelectric stack that is amplified by a horn, and the impacts are hammering a free mass, a mass that is loose, not attached to anything, it's just hopping, just like basketball, and it hammers onto bits. So basically we have a transformer of the high frequency of the piezoelectric stack. In this case, the case that is shown on the right, it's about 20 kilohertz, and it is reduced by the free mass to something like in the range of the hundreds of hertz. And I have a video here that shows the action, and you can see how the fragments or the cuttings are removed, and there is some variety of things that we drilled, and you can see how fast it is drilling into ice. So it's quite effective. And what we did, we took a video camera to the high-speed one to see what's happening in the process so that we can do a modeling of this. And basically it helped us understand what's happening when the horn hit the free mass. And you can see how the fragments are generated and are removed from the hole, or the hole that is being formed. We have won the 2000 R&D 100 award for the most innovative mechanism, because we started around that year. And we have made a lot of versions of the drill. We drilled at very low temperature. This is just a snapshot of some of the things that we have done. But on the right, you can see some of the tests that we have done with our Gopher idea. The tent is a place where we had done a test in Antarctica. And you can see the drilled hole that was done in Antarctica. At the time, we reached something like 1.70 meters. But since then, we have done much more work, and we reached already 3-meter deep demonstration. Of course, we could go even deeper. To have the test of the mechanism, our group is focusing on the piezoelectric side, that is percussive mechanism, while Honeybee is making the whole engineering device from end to end, from the cable all the way to the cutting surface of the bit. The lab version has the rotation actuator on the side because our focus is on the piezoelectric, and we're doing modeling, we're doing tests, and once we have the mechanism produced, we have installed it into we are installing it into the drill itself. We already had a version that we called the Gopher, Auto Gopher 1, and now we are in the next phase. Auto Gopher 1 was just so that we demonstrated the drilling capability, and the removal of the cores has been done by a separate mechanism. Now we are in the full-blown automation of the whole thing. To see what the mechanism look like, it basically has a rotation section and anchor, piezoelectric actuator, and a drill bit. The drill bit here is coring bit, but as I will talk later, we have shifted to an auger instead. Some of the data, here is some of the field data about the operation of the piezoelectric actuator. The advantage of a piezoelectric is you can activate it as soon as you turn, basically it's on. It doesn't need to reach steady state as opposed to an electromagnetic motor that needs a steady state. So as such, we can activate it with duty cycling. And what we found is it's quite efficient if we just use it with the duty cycle of 50%. Means on 50%, off 50%. And what we also can see in this graph, that we're getting basically the same performance of penetration rate when we do the drilling with 1 second on, 1 second off. We tested it in the lab, and we also tested it in the field. Here's a picture of the team that went to do the test at a U.S. gypsum company outside, not too far from JPL. And here's the actual results. This is a close-up here of the drill itself and the coring bits that were collected. Basically, the coring bit depth has been, or the ability to drill each time has been something like 10 centimeters. And you can see that we drilled just short, longer, deeper than 3 meters. And the reason why we stopped is that the length of the cable that we had. Here, as I have video of the drill and the different components, so it's self-explanatory. I will let it have it show the drill. It's an overall view of the drill as it was tested in the lab. It has this anchor, and you can see it in action, opening to secure itself to the wall and provide the anchoring action. In the future, we may have two in order to be able to steer the bit. We have here the extender that allow it to penetrate the distance of the coring bit. This is the actuation mechanism that is based on the piezoelectric. This is, of course, exaggerated for illustration. And this is the rotation in the lab that we've done. So it is illustrating how the action was done. And of course, in the drill itself, the rotation motor is along the axis of the drill itself. And here is a demonstration in the lab. Here is an example of the cores that were formed in the lab. And we did this test in 2012 with the Gopher 1, and as we're currently working on the Gopher 2. Just different views of the drilling that we have done. This is a field test where we drilled the 3 meter deep. The view to the hull, of course, self-speaking. Following this task, we started in this recent development of the Gopher 2 with everything being integrated. The first thing that we focused on was the making of the core breaker. What we have done, we created a mechanism that has a wedge in it, and the wedge basically, once it reaches the length of the core, a coring bit, it starts hammering to the side, and that breaks the core at the bottom. The mechanism did work. Basically, it was in this case an insert that we created for the drill, and but what we found is that we have no way to assure the breaking of the core at the bottom and the ability to extract the core from the hole. So if we cannot assure that, it is a troublesome approach. So this led us to changing strategy and moving to, instead of making cores, making an auger, and it is shown here. We have made, we designed already the auger configuration. We created a 3D model, and we're doing all the modeling needed to optimize the way we're gonna create the fragments and remove them from the hole. Basically, in summary, inspired by the Gopher, wireline drill has been produced and demonstrated. Initially, it didn't have the core the fragments removal integrated. The main feature of it is that it is a feather mounted mechanism that can be attached to a rover or lander to provide power and data communication. Once it penetrates the hole and it forms the fragments to the depth that it can do, the fragments are removed and then it is lowered back again. The mechanism of percussive hammering is basically piezoelectric actuator that drive it to create the hammering, and basically the advantage is that it doesn't need high actual load, so we can operate at really low gravity environments and still perform. The result indicated that it can operate as an effective tool for reaching great depth, potentially hundreds of meters or more, and it could be used in future missions to search for life, water, and whatever NASA will seek. If you want to read more about this mechanism, we published a book in 2009 called Drilling in Extreme Environments, and that here you see the cover page. And with that, I'd like to thank you for coming to listen to my presentation, and I will be happy to answer questions if you send me an email to yosi@jpl.nasa.gov. Thank you very much, and enjoy your stay in Italy. Bye.